This is the Flight Readiness Review for UT Austin. Hi, my name is Blake Younger and I'm the Program Manager here at UAB. I'm a senior in aerospace engineering and I've been on the team for about 2 years now. On the flight line I will be ensuring all checklists are followed and I will also be keeping the time.
Hey, I'm James Bell. I'm an aerospace engineering senior. This is my 4th year on the team. I'm the chief engineer. I've had previous experience with an internship concerning drones and base stations. And on the flight line, I'll be doing general flow and troubleshooting.
Hi, my name is Bradley Bridges, and I'm a sophomore computational engineer. Been on the team for about 2 years now. I'm the systems lead for this year, and on the flight line, I will be maintaining the interop screen and setting up the ground station.
Hi, my name is Hari Kusuru. I'm a junior studying electrical engineering. I don't have much experience with UAVs in general, but I have been on the team for about 1.5 years now, and I am the image recognition lead. And my primary responsibilities on the flight line are to oversee the automatic image classification task.
Hello, my name is Israel Hernandez. I am an aerospace engineering sophomore. I already have 2 years on this team. I have no prior experience with UAVs. I am the sub-team lead for configuration, and at the competition, I'll be in charge of assembly and maintenance.
Hi, my name is Akshat. I'm a freshman aerospace engineering student. I've been on the UAV team for about 1 year now, and I had no prior experience before I joined the team. My role is I'm on the configuration team, and I'm also the mission planner pilot on the flight line.
Hi, my name is Evan Wild. I'm a freshman aerospace engineering major. I have no prior experience with UAVs. I've been on the team for about 1 year now. I'm on the configuration team, and my role on the flight line is air delivery and assembly.
Hi, my name is Rahul Bhutani and I'm an electrical engineering major at UT and a freshman. Prior to joining this team, I had no experience with UAVs, but I've been on this team for about 1 year now, and I'm part of the systems team. On the flight line, my job is maintenance of the onboard computer on the plane, as well as manual image recognition on the ground.
My name is Clayton Lawrence. I'm an aerospace engineering freshman and I have no prior experience with UAVs, but I've been on the team for about 1 year now. I'm on the configuration team, so I'll be helping out with manual image recognition and hardware assembly on the flight line.
Hello, my name is Mark Malmer. I will be the safety pilot for the UT UAV team. I have over 20 years of experience flying RC aircraft, around 10 years of experience flying various sorts of UAVs.
For our plane's mechanical systems, we use the Hugin 2 2.6 meter plane RC kit. It's a pusher prop. It has a 520 kilovolt motor, 100 amp speed controller, and we're using an 18x10 prop, which pulls about 80 amps at full throttle. We use a water bottle dropper, which has been the machine mode of our students, and we've retrofitted the plane to fit that, as well as the gimbal, which is 3D printed here at UT into the plane. We've also got some extra platforms we've added onto the plane and inside the fuselage to give us the ability to do all of our electrical components in it. We also have a Pixhawk 2, which is our autopilot, the Odroid C2, which is a computer on board that we use to communicate with the camera, as well as the ground station. Rocket AC, which is the way that we communicate directly with the ground station. On the ground, we actually have a 15-degree and 160-degree right-hand circular polarized antennas that allow us to talk to the plane, and those are actually on a gimbaled antenna tracker. We have a 3DR transmitter, which allows us to communicate with the Pixhawk 2 and the ground station telemetry. And then finally, we have our software systems, which the FlightView is an in-house software system developed to allow us to store both telemetry and images into a database and serves those up so that we can access them from any computer, allows for manual image recognition, as well as communicating directly with the server. Finally, we have autonomous detection, localization, and classification system, which communicates with FlightView to perform all autonomous DLC tasks.
These are the objectives we plan to accomplish. We have a high probability of getting the mission time, and we think we'll do similarly well in the autonomous flight portion. We have a medium probability of getting the obstacles because we are very confident in avoiding the static obstacles, but are less confident in avoiding the moving obstacles. So for the ODLC, we have it broken down into 5 sections. We've got a high probability of getting the characteristics, medium probability of getting the geolocation since it's less tested, high probability for actional medium probability for autonomy, and medium probability for submitting them over the interoperability network. We have a medium probability of achieving the air delivery task, and a high probability for operational excellence.
For our system, we have to test both the software and the hardware. For the software, we use unit testing to test the server endpoints as well as the database queries. We performed that unit testing using Travis continuous integration, and all unit tests included correct data and incorrect data, and ensured that all incorrect data caused the system to fail gracefully. We also went ahead and used simulation using DroneKit SATL. That allowed us to determine that the system worked properly before actually going to the field, because we were able to use Artplane 3.8. Secondly, for hardware testing, we had to test all the components with component tests before we actually integrated them into the system. That way we can determine if the components would work for the actual mission before we actually got too far down the road. These component tests perform stuff like the camera, the motor, the Odroid, and the transmitter, as well as the PixHawk itself, because we're using the new PixHawk too. Integration tests are important because once you have all those things, ensure they're working properly to make sure they're working properly together. Finally, the flight tests are important because it allows us to do qualification testing for the full system and ensure it works for the competition.
For autonomous flight, so far we have performed 5 autonomous flights, which involves manual and auto takeoff and manual landing. That leads to at least 2 minutes in manual flight. To ensure a successful flight test, we have done tuning and pitch and roll PIDs and yaw to roll mix, which is tuned in a fly-by-wire. During takeoff and landing, we have tested the total energy control systems and determined the stall, cruise, max speeds, as well as the maximum pitch and the climb and sink speeds.
To gauge our waypoint accuracy, we conducted 2 different flight scenarios. For our first flight scenario, we want to see how well our UAV could ascend and descend in order to reach the target waypoints. And so we found that if a waypoint is about a 50-meter change in altitude away, that we needed to be about 183 meters horizontally away in order to reach that waypoint with our desired accuracy. We also conducted a scenario in which we set 2 waypoints 100 meters away from each other, and we saw that on average our entering turn accuracy or error was about 4 meters, and our exiting turn error was about 19 meters. And we also noticed that when we tested at wind speeds of 7 meters per second, which is the maximum wind speed we'll have to see in the competition, that the wind didn't really have a huge impact on our waypoint accuracy.
For obstacle avoidance, our mission planner pilot is simply adding waypoints, moving waypoints, or adding guided points, so we can avoid static and moving obstacles. On our field, we can only fit 2 static and 1 moving obstacles, so our test data was a bit limited. However, we were able to successfully avoid the 2 static obstacles by the moving of waypoints and guided points. However, the moving obstacle was a bit tricky to avoid.
Imaging performance for the UAV has been monitored over 10 test flights with video surveillance and a maximum reception distance of 1/2 mile. Statistics show that a 1-foot target analyzed from an altitude of 250 feet and a field of view for the camera of 30 degrees will yield a image resolution of 7 by 14 pixels. In order to ensure image quality, we've chosen to narrow the radio bandwidth for the camera in order to avoid interference with analog transmitters. Additionally, the antenna tracker is at 15 degrees and 160 degrees in order to avoid point errors. And if all else fails, then upon landing, the images can actually be downloaded from the Odroid on board.
So for the testing of our actual automatic image classification system, we had to look at the accuracy of our deep neural network. And in particular, we had several thousand different images in our training data. And our testing data comprised of only about 27 actual targets. And so most of our training data was actually generated images. With that said, the accuracy was still quite impressive. We had about, as I said, 27 targets to work with. Out of those, 18 were correctly classified, 4 were incorrectly classified, 5 were ignored, and 8 were falsely detected, or also known as false positives. And with this, we've made several different modifications to refine our training data and also change our pre-processing methodology. With pre-processing, for example, we've had to refine our actual edge detection to change the threshold to make sure that we don't pick up as much noise. In addition, we've also noticed that a lot of our false positives were being caused by backgrounds that were either too noisy or backgrounds that were far brighter than our actual training data, and therefore we've had to modify our training data to actually be better representative of our actual flight tests.
For localization testing, we started off in the lab by testing our algorithm for finding the longitude and latitude of the four corners and center of an image, as well as warping the image based on the orientation of the plane and the gimbal for the camera. At the same time, we placed images manually using field data. So we placed the images on a map, and using this method, we came up with approximately 30 meters of error in placing the targets. For our actual algorithm, we estimate an error of roughly 10 meters, and this is altogether this is 10 meters of error, which once we finally implement and integrate our algorithm, we expect this number to go to decrease drastically.
For air delivery, we began with laboratory tests, which involved throwing the water bottle off of our building into a empty construction site. We found that the best solution was a streamer and duct tape to reinforce the water bottle. We then moved on to flight test, where we found the streamer got caught in the motor, so we used strap-in tape, which worked very well. We performed 3 tests with strap-in tape, and from our target point, the water bottle averaged about 10 meters from there.
Our full mission testing proceeded as follows. First we did autonomous takeoff, and then we proceeded to the waypoint navigation phase. Once these waypoints were hit, we proceeded to the search area, where 6 targets were on the ground. These targets had known GPS locations, so that we knew if our location system is working properly. After we found these 6 targets, we proceeded to the air delivery phase, and then the emergent target phase, and finally we manually landed. We plan on autonomously landing at the competition, but our autonomous landing isn't fully developed yet, so we just manually landed. So some things that we've learned from this full mission test, based on our cruise speed of 11 meters per second, we should be able to complete the search area at the competition in 10 minutes. We're expecting the full mission time to take 25 minutes from takeoff to landing, which is good because our plane has a total endurance of 40 minutes. And so if a phase of the mission gets delayed unexpectedly, then we have time to stay in the air and complete that before our plane runs out of energy. What we've learned is that during heavy crosswinds, the plane can fly off course, and we don't want that to happen because we may miss land that contains a target. So we're going to make our flight plan so that it's either flying into the wind or away from the wind. Something else that we've learned is that during long flights, the ESC can get too hot. This is because the ESC did not receive enough airflow, and so we've moved the ESC from its previous location to a new location where it's receiving lots of circulating air to keep it cool. This is something we didn't realize that would happen until these long, 30, 40-minute flight tests. Something else that we've learned is that the setup of the plane is too long. It's too difficult to set up, and it puts the 15-minute setup time at risk. So what we're doing instead, we're going to rework the setup so that we don't need nearly as many screws to assemble the plane, and we're going to streamline the battery installation process to minimize that time.
Our expected score from our mission test came out to 62.5 points. We based that on timeline of 10 points, auto flight of 21.3 points because we lost points from waypoint accuracy, as well as having to go to a manual landing. Obstacle avoidance 10 points based on not being able to dodge moving obstacles. ODLC 4.2 points because we don't have the communication set up for that yet with the server itself. Air delivery 7 points based on accuracy. Operational excellence 10 points based on how cool my team is. 62.5 points.